Hello students, in today's lecture I will discuss about three-dimensional transformation and their matrix representation along with the composite transformations. In the previous lectures we have already seen about two-dimensional transformations. In two-dimensional transformations we are having two axes, that is the x-axis and the y-axis, while in case of three-dimensional transformations we are having one more additional axis, that is called as z-axis. So here you could able to see the figure. In this the figure is a three-dimensional object, and the object would be described by using the three-dimensional coordinate system. This is along the x-axis, this is along the y-axis, and this is along the z-axis. Okay, now we have already seen that there are five types of transformations. First is translation, then second is rotation, third is scaling, fourth is reflection, and the last is shear. Translation, as we have already defined, it is the repositioning of an object along a straight line path. So in three-dimensional transformation, to translate a point in three dimensions by dx, dy, and dz, that means we are changing the position of the object along a straight line path, and the object is basically, it is a three-dimensional object. So the changed positions could be described in the form of translation vectors, that are dx, dy, and dz. And we could able to calculate the new coordinates simply by using these three equations, that is x dash is equals to x plus dx, y dash is equals to y plus dy, and z dash is equals to z plus dz. So here in the figure you could see that we are having one pyramid, and pyramid is basically, it is a three-dimensional object. This is the original position of the object. Now we are performing translation, that means we are moving the object along a straight line path. So these are the new coordinate positions or the translated positions of the object, and x, y, z could be represented in the form of x dash, y dash, z dash after transformation. Now second is scaling. Scaling is defined as changing the size of an object. Either we could increase the size of an object or we could reduce the size of an object. For scaling we are having the scaling factors. To scale a point in three dimension by xs, sx, sy, and sz, we could simply calculate through the equations as x dash is equals to sx into x, y dash is equals to sy into y, and z dash is equals to sz into z. So these are the scaling factors. In translation we are doing addition, while in case of scaling we are doing multiplication. So here you could able to see that we are having one rectangular pyramid, or it could be a triangular pyramid, and this is the initial position of the object. Now we are increasing the size of the object by applying the scaling factors. So here you could able to see that the new positions becomes any point at this position having the coordinate x, y, z would become x dash, y dash, and z dash. So here the scaling factors values are more than 1. That's why the size of the pyramid has been increased. If we are keeping the values as less than 1, then it could reduce the size. If the values are equals to 1, then there is no change in the size of the object. And in this also we have discussed about uniform scaling and differential scaling. If sx, sy, and sz values are equal, then it is called as uniform scaling, while in other case it is called as differential scaling. Now rotation. Rotation is basically, it is again changing the orientation of an object along a circular path. Whenever we are changing the orientation of an object along a circular path, then it is called as rotation. Okay. When we perform rotations in two dimensions, we only had the choice of rotating about the z-axis. In the case of three-dimensional axis, we have more options. We could rotate the object about the x-axis, we could rotate the object about the y-axis, or we could rotate the object about the z-axis. So here we are having three choices. Either we could rotate the object about x-axis, y-axis, or about z-axis. So these are the transformation equations you can see for the three-dimensional rotation. The equations for the three-dimensional rotations are described as following. And here we can see that if we are performing rotation about z-axis, then certainly it will not change the value of z. So x dash is equals to x cos theta minus y sin theta, and y dash is equals to x sin theta plus y cos theta. It is similar to two-dimensional rotation, and which we have already seen in the previous lectures. If we rotate the object along the x-axis, then certainly it will not change the value of x. So x dash is equals to x, y dash is equals to y cos theta minus z sin theta, and z dash is equals to y sin theta plus z cos theta. While if we are rotating the object along the y-axis, then certainly it will not change the value of y. X dash is equals to z sin theta plus x cos theta, y dash is equals to y, and z dash is equals to z cos theta minus x sin theta. Now, homogeneous coordinates in three dimension. We have already seen in the previous lectures, whatever equations that we are dealing, we are representing all those equations in homogeneous coordinate system. Why we are representing? Because whenever we are representing the equations in homogeneous coordinate systems, all the equations becomes homogeneous. That means their dimensions are same. Matrix of translation, whether it could be a matrix of rotation or scaling. So we are representing the object matrix in the form of columns. For example, if we are having any point x, y, z in homogeneous form, we are representing this point as a column vector in the form of x, y, z, 1. So this is the way of representation of any point along the column. If I am having line, then I could able to represent it like this: x1, y1, z1, 1, x2, y2, z2, 1. So this is the notation that we are following in homogeneous coordinate system. Okay. So here you can see that the dimensions of all the matrices are same. The matrices are of dimension 4 cross 4. So the translation matrix would become 1 0 0 dx, 0 1 dy, 0 0 1 dz, 0 0 0 1. Okay, the scaling matrix will become sx 0 0 0, 0 sy 0 0, 0 0 sz 0, 0 0 0 1. And these are the rotation matrices about the x-axis, about the y-axis, and about the z-axis. Three-dimensional composite transformation. Whenever you are performing more than one transformation, then it is called as composite transformations. The examples could be rotation about pivot point and scaling about fixed point. Even reflection about the line y is equals to mx plus b is also an example of composite transformation, and these composite transformations we have already seen in the two-dimensional transformation. So this is all about today's lecture. Thank you.